Well, I've been a senior for like 4 years, so.
Okay. When I first heard that term super senior, like, I thought that's supposed to be a good thing. Maybe they need to find a different adjective for that.
Exhausted senior.
Senior.
Yeah. Okay, so
Slow senior.
Senior.
So as I was talking about, like we have, the test coming up on Friday, but we will certainly have Wednesday set aside to do any sort of review for that. But in the interest of not falling behind, I do need to start this next section, and then we'll, whatever I don't get to it today, we'll pick up on after the test. And I may set aside some of today for review. We'll see how it goes, because I also want Wednesday as an opportunity for any homework questions, since there's a homework due Wednesday night. Okay.
I didn't know.
And that homework is relevant to the test.
The whole, oh yeah.
Okay. Now, this deals with something I hope you dealt with in Cal 3. It's hard to tell. It seems that whoever's teaching Cal 3, that might affect what's actually covered in it. So what we get out of line integrals is a way to take a formula that you would have seen like in a physics class and how to generalize it to more situations. So in physics, you learn about the concept of work. And I don't suppose anyone actually remembers what is a simple formula for work done in when an object is moved.
Force times distance.
Force times distance. Okay, but generally this formula only applies if the force is applied to an object to move it over a certain distance, and the work done in moving an object is assumed here that the path of the object is a straight line. But what happens if not? What if an object is being moved along a curved path? What is the work being done in that case? So you have some curved path along which the object is moving. What is the work done in getting the object from point A to point B? To figure it out, of course, we need a way of describing curves. And since this formula is a product, the way product formulas tend to be generalized is using an integral. So just as mass equals density times volume, if you're integrating the density over an object, then you're applying that same formula at each point to get the mass. And this is going to be very similar. So the way I'm going to describe this curve is parametrically. So the way we'll most often describe a curve C is using, as I discussed last time, a vector valued function, R of t. So for each value of t, we have components, x of t, y of t, z of t. Or we might just scale down to 2 dimensions and have only x and y. And t, the parameter ranges between a and b. So we literally have point A and point B. So this initial point corresponds to t equals A, and the end point corresponding to t equals b. Okay. So most of the time, we'll describe curves in this way. Sometimes we might be able to do it a little more simply. For instance, if we're in a plane, we might be able to describe a curve y as a function of x. So you can think of x and t being the same thing in that case. So if you were to divide a curve into many small segments, then you could think of each of these segments as essentially being straight lines. It may not be exact, but of course, as you make your segments smaller and smaller, that's a better and better approximation. So you can think of this curve as infinitely many line segments that are infinitely short, being glued together. So if I were to zoom in on a portion of this curve, so here's a certain point along the curve, and the curve is actually behaving like this. It's not quite a straight line, but very close to it. And you're approximating it by this line segment. So you can think of now, if we think of this line segment as having a length called delta S. So we're going to be using S as our variable of integration, ultimately. So along each segment, we can go ahead and use this simple formula. Work is equal to force times distance. So if I let my integrand f of x, y, z represents the force that's being applied at that point along the curve. Actually, I'll use a large F for this. Okay. Then the work that's being performed to move the object along this portion of the curve, so from here to here, is essentially going to be equal to that amount of force, and I'll call this point R of T1. This point is R of T2. So we're letting T vary from A to B. Starts here at T1, ends here at T2. So I would evaluate the force at some point along the curve, let's say T1, or any point in between. This is just an approximation, times the distance, delta S. So on each segment, we're using a simple formula, work equals force times distance. But we need to express all of this in terms of parameter values. And right now, we don't have an easy way to do that with this delta S. So here's what we can do, like from a two-dimensional case. If I draw a right triangle here, well, this is delta x for a two-dimensional case, and then delta y over here. So now I can express this as my force times square root of delta x squared plus delta y squared. And now what I can do is, if I multiply and divide by delta t. Now, the delta t in the denominator, I'm going to move inside the radical. That's going to make it delta t squared. So I have delta x over delta t squared plus delta t over delta y over delta t squared. So this becomes, as delta t goes to 0, I have my force evaluated at a certain point, r of t, times the square root of dx dt squared plus dy dt squared. That's something I can compute because these equations, the parametric equations of a curve, that's something that would be given. So if I want to get to work over a single segment, there's supposed to be a delta t on the outside of the square root here. So this would be, and again, this is not under the square root. There's a dt here. So what I can do is that gives me,
Thank you.
bless you, work along one segment. So if I want to work along the entire curve, I'll just be adding these up. So we get an integral. So because this is the work along a infinitely small, short segment, where that length is dt, and the integral has the effect of adding all of these up. So now I can give you an integral formula, the first of several we'll see in this chapter. So the line integral of some function f of x, y, z. And I want to emphasize this is a scalar valued function because there's no vector symbol here. Along a curve C is, so there's, the way this is generally written is we have a curve that we're integrating over written below the integral sign, and we have f of x, y, z ds, where ds corresponds to arc length along the curve. But of course this doesn't help you to evaluate. So what you actually evaluate is the integral from a to b. So you have your parametric equations. And you substitute your parametric equations into your integrands. And then you multiply this by the square root of the sum of squares, which is this whole square root expression here is the magnitude of your tangent vector. Okay. So another way of writing this, it's a little more compact, is f with your parametric equations plugged in. So that's x of t, y of t, z of t as a vector. And then what you have here is the magnitude of r prime of t. So if r of t gives you your points along the curve, that's your position function, r prime of t is your tangent vector. Okay. So that's what a line integral of a scalar valued function is. And if your function f indicates force, then the line integral of f along the curve is the work done in moving the object along the curve C. Okay. So that's just how to interpret that line integral. Okay. We actually have two formulas for line integral. It's line integral of a scalar value function, which is what I've shown you, but also for a vector field will come from this. Now, as an example of how to do a line integral, So here's your integrand, so we're in 3 dimensions, so x squared z. And the curve, this kind of problem will come up often, is just a line segments from with given endpoints. So the starting point is 0, 6, minus 1 to 4, 1, 5. Okay. So we're not given parametric equations for this curve, although from the endpoints you can easily come up with one. So what you can do is get the direction. And since it's only a line segment, the direction along the line segment is going to be constant. It's going to have a constant tangent vector. So what you do is, we'll call this B, you subtract the final minus initial. So 4 minus 0, 1 minus 6, 5 minus minus 1. So we get 4 minus 5 and 6. So from this starting point, you're heading along the direction of this vector to get to this final point. And so then your parametric equations would be your initial point, 0, 6 minus 1, plus your parameter t times your direction. So t times v. So this here is your initial point. Okay. And t goes from 0 to 1, because if t equals 0, you're at the initial point. If t equals 1, then you're going to plug this vector into here, and adding these two together will get you to your final point. So 0, 6 minus 1 plus t times your direction, 4 minus 5, 6. So now we can write down parametric equations for x, y, and z individually, just by looking at the components. So for instance, x is going to be 0 plus 4t. And what about y? So we've done x, y, and z in order.
Well, is it just going to be 6 plus negative 5t?
Yeah, 6 minus 5t. And finally, z?
Negative 1 plus 6t.
Yeah, minus 1 plus 6t. So these are your parametric equations for t going from 0 to 1. So once you have the parametric equations, then you're able to set this up as an integral with respect to t. In this case, t will go from 0 to 1. That's an awful eraser. Okay. Well, goes with a lousy chalk. Okay, just make sure that showed up on the screen there. Okay, so this line integral, x squared z ds, now becomes the integral from 0 to 1, and now we can fill in x, which is just 4t. Oh, let's get the attendance going. So we have 4t squared times z, which is minus 1 plus 6t. I'll write it as 6t minus 1. And then you have the square root of your derivatives. Well, so x is, that's 4t, and this was 6 minus 5t, and then minus 1 plus 6t. So so what are my derivatives? What are my parametric equations?
For that, it's just going to be x, the derivative of 4t is going to be just 4, -5, and 6.
Yeah, so when it's a line segment, it's just your direction vector. Those are your derivatives with respect to time. So now you can go ahead and throw these in here. So 4 squared plus minus 5 squared plus 6 squared dt. One of the difficulties of this integral formula is that because of a nasty square root expression, that can make integrals very difficult. So often you see cases that happen to work out very nicely. So at least that's just going to be a constant that can be pulled out. So this turns out to be square root of 77, and then integral from 0 to 1 of 24t cubed minus, 96t cubed minus 16t squared. Okay. And at this point, it's a single variable integral. And I will refer you to these pages for notes to see this worked out in default. Again, just like from a previous chapter, it's the setup. So you give a description of a curve, you get the parametric equations if those are not given to you up front, and then the derivatives go here to sum of squares, and then you take these and substitute them into your integrand. Any questions about this one?
That is a thing of beauty.
What? Oh.
That's a thing of beauty.
If you say so. All right. Now. Okay.
And were you given that t was between 0 and 1, or did you figure that out?
Oh, sorry. Which one? That's just from a way I set up the equations of a line. So if you're given a line segment in terms of here are the endpoints, and you do it that way by subtracting the 2 points to get your direction vector, then yes, t will always go from 0 to 1 in that case. And it's just because my parametric equation starts with the initial point plus t times something. So if t equals 0, I get the initial point. And if t equals 1, then you get initial plus final minus initial. So it can't. So it simplifies to a final point. So yeah. So if you handle line segments that way, yes, it's always 0 to 1. But in other problems, like the one I'm about to do, the t values are just given to you. Okay. So for this next one, here's our line integral, 2x plus 9z. Yes. And here parametric equations are just given. So x is equal to t, y is t squared, z is t cubed, and t goes from 0 to 1. That has to be the case in these examples. It will not always be like that. So one thing you know you'll need is, just like in the previous example,
The derivative.
you need a derivative, but quite easy to handle in this case. 1, 2t, 3t squared. So, so now your integral will be from 0 to 1 in t, and then you have 2x plus 9z. So you go ahead and fill that in. and it's a good idea to put parentheses around it. And then you have a square root of x prime squared plus y prime squared plus z prime squared dt. So now everything's filled in. Question is, this is something that can be integrated. So now we have 2t plus 9t cubed. And then when you handle the squaring over here, you get 1 plus 4t squared plus 9t to the 4th. Okay. Now, this seems like it'll be quite a pain to handle. So how might you try integrating this?
With the substitute.
Yeah, so
Under
substitution.
the radical.
And what?
Would you use what's under the radical?
Yeah, so it's under the radical. So 1 plus 4t squared plus 9t to the 4th. But therefore, du is what? 8t plus 36t. Yeah. Cubed. Yeah. dt. Now, what's interesting is this is exactly 4 times that. So in fact, I'm going to write it that way. I'm going to factor a 4 out of this. 2t plus 9t cubed dt. So that way, this and this, everything I've underlined there, that's just going to become du over 4. So I have 1/4, and then we'll have u to the 1/2 du, and then you can plug in the limits. So if t equals 0, u is equal to 1, and if t is equal to 1, then you get u is equal to 14. So if you want to do the limits that way, that's how you would handle it. You plug in your original limits into your substitution, and what you get out is u. Those are your limits in the new integral. And then this is on page 110 to work that out. So it's 1/4, 2/3 u to the 3/2 from with limits 1 to 14. Or you can put it back in terms of t and go back to your original limits of 0, 1. I don't care how you do that. So then you can finish it off with your calculator from there. Okay. Now, of course, if these constants had been even a little different, then the substitution would not have worked. Yeah, that's not just B's problems, it's all contrived. But then, really, this is, in fact, I had a spirited discussion of Dr. Schroeder as to whether we should even cover these. But I would point out we're meant to set up the upper kind of line integral, which actually that'll have to wait until after the test. But any questions of any questions about this one? Okay. I should mention so how this can be used for work. I'll give one other application. Okay, so we have center of mass of a wire, and where the wire is your curve C. And as before with mass, I'll let rho refer to, rho of x, y, z refer to the density at any particular point along the curve. So your mass, m, like before, would be the integral of the density. So you just integrate that and evaluate the same kind of line integral. So the center of mass would be x bar, y bar, z bar. So x bar would be 1 over the mass times the integral, the line integral over the curve of x times rho. And then for the y coordinate, integrate y times rho, and then z times rho, etc. So, so the same formulas that we saw for center of mass of other objects apply equally well for center of mass of a wire. All right. In case that comes up in the homework, I don't remember what I put there. Well, it's 2 years ago. So checking, okay, these problems, oh, that's too many. And, okay. Now, well, does anyone have questions about the upcoming test? Certainly you take time for that.
Hold on, let me get on my list.
How long a list are we talking about?
I was just going to ask you to go over number 6.
Oh, okay. Oh, yeah, I kind of figured that would be troublesome. Okay.
And that's on the practice test.
Okay. Okay. So you're integrating e to the x where your region R is a parallelogram. Okay. So the picture that's given is the equation of a line. So this one is y minus 2x is 0, y minus 2x is equal to minus 3. Although, that's what it says in the, 2x, 2y minus x equals 0. And then 2y minus x is equal to, what is this? Okay, all right. Now, I'm going to rearrange this a little bit, because I can also say 2x minus y is equal to 0. And if I negate both sides of this, I can say 2x minus y is equal to 3. So when you have a situation where, particularly that's for a parallelogram, where you have the same function of x and y for opposite edges, there's equal different constants for these edges and a different one for these edges. And so you can set u equal to the left side of one set of edges, so like u is equal to 2x minus y to cover these edges, and then v for the other one set of edges, 2y minus x. Now, so this would be like a generic way of how you handle a parallelogram once you get the equations of all the edges. In this case, those equations are given to you. But then it's the constants involved. Whatever's on the right side, that gives away the limits. So your limits for both actually would be 0 to 3. So it gives you a natural way to change this region. So it's a parallelogram in x and y, but it's simply going to be a rectangle in u and v. So what you're going to get is integral from 0 to 3 in u is 0 to 3 in v, e to the x, but now you have to invert these equations. So you have u and v in terms of x, y. Now you need it to be the other way around. So what you can do is, from these equations, I could say that I'll use the second equation. X is equal to 2y minus v, which you then substitute into the first equation. So 2 times 2y minus v minus y, because now x has been eliminated. So we have 3y minus v, and now you can solve for y. So y is equal to...
Is it not 2v? U equals
yes, it is 2v. Okay, so it's u plus 2v all over 3. And now you can take that and substitute that. So when you have these linear equations, it really is just elimination and substitution.
How did you go from u equals 2 times 2y minus v minus y to the u equals 3y minus 2v?
I just multiplied this out. So 4y minus y.
Okay. Yes, okay. I didn't see it.
So then for this, x is 2 times u plus 2v over 3 minus v. So you're going to get 4v minus 3v. So it ends up being the other way around. 2u plus v over 3 once you simplify all of this, because this would be, so that would be 3v over 3, just to give everything a common denominator. So we'd have 4v minus 3v would give us v. So now you have x equal to that.
So we have e to that.
Yes. 2u plus v over 3. And then we need the Jacobian derivatives of x and y with respect to u and v, dv du. So there's still the Jacobian to figure out. Fortunately, in this case, all your derivatives are constant, because x and y depend on u and v linearly. So we'd have dx du, dy dv, minus dx dv, dy du, and don't forget to take the absolute value. This has to be positive. So dx du would be 2/3. dy dv is also 2/3 minus xv, which is 1/3, and dy du, which is 1/3. So we get 4/9 minus 1/9. So we end up with 1/3. So 1/3 is what goes in here. So that's where that factor comes from. And this problem only required you to set it up, not to evaluate it. And the real test will be the same way. We have to set up, we'll get it into the new variables completely, but then you can stop there. This integral could be done. It'd be kind of a pain because of all the fractions, but it can. Basically, you would break this up into a product, like e to the 2u over 3 times e to the v over 3, and you can integrate those separately. So from the description of a region is where you can get your new variables. If a change of variable is not already given to you, which in some problems it is, and I'm refreshing my memory as to what I put in the real test, because just because this is a parallelogram problem doesn't mean that you should be anticipating a parallelogram problem on the real test. But what you can expect to do is work out changes of variables, figure out a Jacobian, figure out what the limits are. All those generic concepts apply. And what I'm doing right now is looking at the problem I put on the real test. Okay, I'm sorry. What was your question?
Would it matter which one we did first in the DV and DU? Like, if they weren't exactly the same, like if they both didn't go 0 to 3, would it matter which one we did
The only
first?
time, not in this case, because the limits for both are constant. And you can always do it in whatever order
You want to.
But yeah, if it turns out that like for instance, the limits for v depend on u, then u has to be the outer
First.
integral.
Oh, okay.
Yeah, so it's the same constraint as before we had changes of variable of x and y. Any other questions?
If you quickly go over number 3.
Okay. Sorry, I want to take a thing. Okay. So. The last comment on this one. So, if you would change a variable from some region R to a new region R tilde, your integral, your original integral becomes an integral over the new region with the new limits. So you always have that substituting into the integrand, and then your Jacobian where that is dx du, dy dv, minus dy du, dx dv, absolute value. So know this. Every change of variable integral involves this. Now, the particulars may be different in terms of what the region is. Okay.
For polar coordinates, it just goes to R, right?
Right.
So my main issue was how am I supposed to know that the R equals 4 sine theta occupies quadrants 1 and 2?
Because because if you're not sure what it looks like, start with theta equals 0. See what happens. When theta equals 0, R is 0. You know you're at the origin. See what happens. At what point do you get back to the origin? When sine theta is equal to 0 again, at pi.
Okay.
So, because you end up getting positive values of r. Right here is where theta is equal to pi over 2. Here is if theta is equal to theta, not pi. Theta is equal to 0 and pi.
And the radius can never be negative. That would also be.
Well, at least not in this equation, yeah. Yeah, if I had been dastardly and said r equals minus 4 sine theta, yeah, that would put you down here. Except then, whatever values of theta you're plugging in to get the curve, those are still the ones you use for your limits. Okay. So the idea is, if you are, back to this, so to keep in mind for a real test, you're not going to get a parallelogram. I promise you that. What you will be given is functions of x and y, just like these are functions of x and y that describe the edges of parallelogram. It's just these are linear functions. you will be given functions of x and y that describe the boundaries of a region in a problem on a real test. So you can use those equations to get u and v in a similar manner and get the limits in a similar manner. It's just that the particular kinds of functions you're dealing with will be different. And again, only set up the integral. You don't, right, don't waste that time. Okay, so these problems in practice are meant to give you the general idea. I don't want any mishaps like on the first test. Like assuming there are 4 critical points or something like that, just because the practice problem had that. Just so you see what kind of questions are coming your way. And we can spend more time talking about that on Wednesday.